We have now realized that the deformation of materials is through the slip or dislocations in slip planes. If you consider that, we also realize that if we want to make a material stronger, we should hinder the dislocations to slip in the planes. We should do some kind of efforts to decrease the slip possibilities for the dislocations. So if we go to strengthening mechanism and hardening mechanisms, we will see how we can do. Here we see a schematic picture of a slip plane. In the top picture here we see a slip plane with no obstacles at all. It's a pure metal, a pure material, and the dislocations can slip here without any problems. It means that we'll have a very soft material with low strength. But if you go down here, we see some other atoms, and that's a result of an alloying. We have put in some alloy elements, and here it looks as though these atoms are the same size as the mother atoms. But if the sizes are very different, the effect will be stronger. So it's very important here what type of alloy element we put. But we can anyway imagine that these extra alloy element added here will influence the slip of the dislocation. Here down to the right, this is a larger thing. This is a particle. And you can add a particle in different ways. It can be precipitated into the material. It can be added directly into a melt from outside. And of course, when you see large particles, there will be an obstacle for the slip of the dislocations. This technique to harden material is called solution hardening, as you solve another metal into the metal matrix. This is called precipitation hardening or particle hardening. Here we see a case where a dislocation line has been passing halfway through a material with solution hardening. You can see the solute atoms here in the area where the dislocation has already passed by, and we can see the solute atoms here in front of the dislocation line. And we can see that when the dislocation trying to pass the solute atoms is hindered partly and it's bent out. It means that new dislocation line is formed, and that takes some force, and that means that it will be harder for the dislocations to slip through the material with these solute atoms, and the material will be harder. Here we have the corresponding situation for the precipitation hardened material. We can see the dislocation line moving here. When it's hindered by the particles, the dislocation line bends out, and it needs more force for the line to move forward here. It means that the material becomes harder and stronger. Here is an example of another hardening mechanism. And here is dislocation themselves that actually are a hinder for dislocation to slip. If you look in this plane, we see here dislocations in front of the dislocation line, and here we have dislocations that have been passed by this dislocation line. And we see on these past dislocations that they have a jog in the shape here in this plane. It means that when the dislocation line comes, there will be a hinder for the dislocations to slide. It means that dislocations hinder themselves. And it means also that, as we remember, if you look at the crystal structure, that there are many different slip planes in the crystal which are crossing each other. So there are different families of dislocations moving in different directions. And when they cross each other, we get this type of jog effects, and we get the effect the dislocation slip is hindered. Therefore, many dislocations in the material will make a harder material. And we call that deformation strengthening, and we'll come back to that later. We have now briefly discussed 3 different strengthening mechanisms and gone principally through also how the strengthening works. There is also one 4th mechanism, namely grain size reduction. We will now start to go through all 4 strengthening mechanisms in more detail and take one at a time.